Imagine standing in a silent field beneath a night sky so clear that the Milky Way appears like a river of powdered light. You look upward, and the darkness feels endless. The space between stars looks like perfect nothingness. Yet physics tells us that this apparent emptiness is the most important something that exists. It shapes the paths of planets. It carries the flow of time. It holds the universe together. We call it spacetime, not space, not time, but a single four-dimensional entity that bends and curves like a living thing. It sounds smooth and calm, but the deeper we investigate, the stranger it becomes. Long before Einstein, space was treated as a stage that never changed. Time was imagined as an invisible clock that ticked forward the same for everyone. Newton's laws worked so well that this picture felt final and complete. Then Einstein came along and asked a bold question. What if the stage can move? What if time flows differently depending on where you are? What if gravity is not a pull from afar, but the bending of this stage itself? He merged space and time into one idea. Spacetime. Matter tells spacetime how to curve. Curved spacetime tells matter how to move. A planet does not fall toward the sun because a force drags it. The planet is simply following the shortest possible path through curved spacetime. That insight changed everything, but it left us with a metaphor that many people still misunderstand. We talk about spacetime as if it were a flexible fabric, something you could stretch or pinch with your fingers if only you were big enough. We imagine a ball pressing down on a trampoline. We imagine ripples spreading across a pond. Helpful pictures, but misleading ones. A trampoline is made of threads woven together. A pond is made of water molecules. These materials exist within space. Spacetime cannot exist within something larger. It is the definition of where and when everything happens. So what is it made of? Does it have parts? Can you cut a piece of space the way you cut a piece of cloth? If you zoom in far enough, do you find tiny atoms of geometry? Or does the smoothness continue forever? In Einstein theory, there is no bottom layer. Distances and durations can be divided again and again without limit. The geometry remains smooth no matter how deep you go. But this clashes with the other great theory of the universe, quantum mechanics. The quantum world insists that nature comes in indivisible chunks. Light arrives in packets called photons. Energy has a smallest step. Motion has a smallest action. The very concept of measurement becomes fuzzy at extremely tiny scales. The universe refuses infinite precision. If space and time truly have no smallest scale, then quantum mechanics and general relativity cannot both be correct. When we push Einstein equations to their limits, they break. In the center of a black hole, or at the first instant of the Big Bang, the equations predict infinite curvature, infinite density, a singularity. That is nature saying stop. The theory no longer applies. Something fundamentally new must take over at that point. Physicists believe that at a scale called the Planck length, which is about 1 decimal point followed by 35 zeros of a meter, the familiar picture of geometry dissolves. You could not measure a shorter distance. You could not define a sharper point. Time itself becomes uncertain. The continuous fabric idea is only a useful illusion when you are large compared to that unimaginably tiny scale. John Wheeler imagined that at this depth, spacetime would look like a frothing sea of fluctuations, little bubbles of geometry appearing and disappearing, pathways stretching and snapping, a quantum foam. Yet even that image might lead us astray because foam is still a material made of something inside space. The reality may be stranger than our words can hold. Worse still, our common metaphors sneak in contradictions. The famous picture of a bowling ball warping a rubber sheet uses gravity to explain gravity. The sheet sags downward due to the planet weight, but that sagging is caused by the very gravitational field we are trying to understand. It is a circular explanation disguised as intuition. Spacetime does not sit on anything. It does not bend because something pushes it from outside. The curvature is simply a change in the relationships between events. It is geometry itself. To really grasp the idea, imagine two lightning flashes, one far away near a distant galaxy, one right here near your hand. Einstein discovered that the separation between these two events is not just distance plus time. It is a single quantity called spacetime interval. This number decides what can affect what. If light has enough time to travel from one flash to the other, they are connected in a deep physical sense. If not, they might as well exist in separate realities. Geometry becomes the ultimate judge of causality. This idea that geometry can determine what is real and what is not is both elegant and unsettling. It suggests that spacetime is more than a passive stage. It is a set of rules that everything must obey. But rules must come from somewhere. Something must enforce them. When we peer closer to the heart of gravity, we find signs that the rules change. They flicker, they clash, they demand new principles. Principles that might reveal what spacetime is built from. Because if spacetime can curve, can twist, and can ripple, then perhaps we are seeing hints of structure beneath the smooth surface. And if there are waves traveling through spacetime, then maybe the waves themselves carry the secret of what spacetime is. Only recently have we gained the power to listen to those waves. Gravitational waves. They are not vibrations of air or water or any familiar substance. They are oscillations of the geometry that defines reality. When massive objects move violently, they send out faint tremors that travel at the speed of light. These tremors stretch and squeeze the very distances between everything. They do not travel through spacetime. They are spacetime changing shape. A century after Einstein predicted these waves, scientists built a detector delicate enough to sense a ripple that changed the length of its arms by less than the width of a proton. In the year 2015, the first detection came. Two black holes spiraled together more than 1 billion light-years away. Their final collision sent a pulse that touched Earth and whispered Einstein truth into our instruments. Spacetime is alive. It is dynamic. It can ring like a bell. This discovery suggests a new possibility. Perhaps spacetime is not a backdrop at all. Perhaps it is a network, a structure that can vibrate, a system capable of storing and communicating information. And if that is true, then gravitational waves might be the most direct clue we have about what lies beneath the smooth geometry. The quest to understand the atoms of spacetime is the ultimate scientific adventure. It forces us to confront the limits of our imagination. It demands that we question the familiar pictures that once guided us. It invites us to embrace a view of the cosmos where the stage is as active and mysterious as the actors upon it. So the question grows louder. What is spacetime really made of? And if it is built from deeper elements, could gravitational waves reveal them? Somewhere in those faint ripples may lie the first hints of the smallest structure the cosmos has ever known. The discovery of gravitational waves was not only a technological triumph, it was a philosophical shock. Until that moment, spacetime felt abstract. A mathematical idea, something you could write in equations but never touch. The moment those faint ripples arrived, spacetime became physical. You could feel the universe breathing. You could measure the heartbeat of black holes. You could listen to the music of gravity itself. But what exactly is doing the vibrating? What is the substance that carries these waves? If spacetime were nothing more than relationships between events, then how can relationships vibrate? How can emptiness swing back and forth like a violin string? Instruments need strings to vibrate. Air needs molecules to vibrate. So what vibration carries the rhythm of these waves? Einstein equations simply say geometry changes. They do not say what geometry is made of. We are left in a situation similar to ancient thinkers trying to understand the wind without knowing what air is. They felt its push. They heard its sound. But they could not yet see the molecules creating the motion. We now stand at a similar edge. We can detect gravitational waves. We can trace them back to cosmic collisions. But the medium that ripples remains hidden. It refuses to break into visible parts. At the human scale, space-time might as well be perfectly smooth. Even at the scale of atoms, perfectly smooth. Only when we approach the impossibly tiny Planck length does our current math lose its grip. The closer we get to the roots, the less we understand the tree. The behavior of gravitational waves tempts us to imagine that space-time has structure like a web. When a wave moves through, the web flexes. If the web threads were more fundamental than space itself, then the ripples would reveal how the universe knits together. But if the web is continuous with no smallest knots, then the wave might simply be a change in pure geometry with no deeper machinery. In everyday life, we forget that space and time are inseparable. We think of distance as something you can measure with a ruler. We think of time as something a clock counts. But in space-time, distance and duration dance together. When you move, your passage through time slows. When gravity is strong, time itself stretches. The entire universe is like a flowing landscape, bending and shifting under the influence of mass and energy. This dynamism suggests that space-time may behave more like a fluid than a fabric. Imagine a river. It looks smooth from far away, but dip your hand close to the surface and you can feel the rushing turbulence. Beneath that, you might find tiny vortices and swirling currents. At even smaller scales, molecules collide and scatter. If space-time is fluid-like, perhaps the smooth geometry we know is only the surface of something restless, something granular, something where the shortest distances are not straight lines, but jumbled networks constantly reconfiguring themselves. The challenge is that we cannot simply scoop up a bit of space-time to analyze it. We live inside it. We are built from it. We have no external vantage point. Every measurement we perform uses space-time itself as the measuring tool. It is like trying to understand your own mind using thoughts that depend on that mind. Quantum mechanics teaches us that when you zoom in, nature becomes discrete. Yet general relativity insists that geometry is continuous. These two masterpieces of human understanding seem to point in opposite directions. They cannot both describe the deepest truth. Beneath the tension between them lies a mystery that gravitational waves could help solve. Consider the energy carried by a gravitational wave. It can shake planets. It can heat matter. But the energy is extremely weak compared to other forces. Why is gravity so feeble? If space-time were made of tiny quanta that respond only faintly to mass and motion, that could explain why gravity is gentle while the quantum world is wild. A difference in the strength of interaction might reveal a difference in how reality is constructed at its base. There is another remarkable aspect of gravitational waves. They travel without scattering. Light waves bounce off dust and atoms. Sound waves fade as molecules collide. But gravitational waves pass through stars. They pass through galaxies. They carry information from the deepest inaccessible places without losing clarity. A message in ripples that nothing can stop. Why are they so pure? Why do they pass freely through everything else? Perhaps because they are not traveling through space-time. They are the behavior of space-time itself. If reality is built from something smaller, those elements must be able to coordinate perfectly across cosmic distances to guide such waves. They must align their vibrations like a perfectly tuned chorus, even when scattered across the universe. That level of coordination hints that space-time might be a coherent system at its smallest level. A network of information rather than a physical material. One more clue comes from the expansion of the universe. Galaxies drift apart. Space stretches. But what does it mean for space to stretch? Does more of something come into existence? Does the web gain new threads between galaxies? Does time create fresh geometry from nothing? Energy is not supposed to come from nowhere, yet the expansion of space appears to create more vacuum energy as it grows. If space-time has a quantum foundation, then this expansion might be a property of that foundation itself, not a phenomenon happening above it. Everywhere we look, the universe hints that space-time is active. Not solid, not fixed, something dynamic that can bend, ripple, stretch, and maybe even grow. Something that can store information, something that can carry signals that no ordinary matter could transmit. Gravitational waves move us closer to answering the oldest question of all. What is space? Not what fills it. What is it? And what is time? That relentless river toward the future. Could both emerge from deeper laws that do not resemble anything our senses can detect. The path forward requires daring science, new instruments beyond our current imagination, new mathematics beyond the comfort zone of classical geometry, perhaps new metaphors entirely. The ones we use now helped us uncover the rules of planets and stars. The ones we invent next may reveal the true architecture beneath existence. We have heard only the first faint sounds of space-time playing its hidden symphony. The echoes arrive from collisions that happened when dinosaurs walked Earth. The universe is speaking, and we have finally learned how to listen. The universe is ancient and enormous, yet gravitational waves allow us to touch events across both distance and time. When those waves reach us, they bring a piece of history. They reveal how space-time behaves when pushed to extremes. What once seemed impossible is now becoming a method of cosmic archaeology. Every wave that arrives carries information about places we can never visit. The cause of merging black holes, the collapse of massive stars, perhaps even the first moments after the Big Bang when the universe itself was a newborn. These waves prove that space-time can ring like a stretched surface struck by cosmic forces. The question that haunts physicists is whether this ringing reveals the structure of the surface. Imagine tapping a bell. The sound tells you if the bell is cracked or pure. If space-time has little grains or threads or nodes, the vibrations might carry that signature. Tiny irregularities could affect how waves travel. Different frequencies might behave differently if they interact with a deeper texture. So far, every gravitational wave we have measured behaves exactly as Einstein's smooth theory predicts. But our instruments are still young. We have heard only the loudest signals. Those are like thunderclaps. What we need to detect next are whispers. The search for smaller and subtler waves has already begun. Scientists are building detectors that stretch for many kilometers. Others plan instruments in space to listen for waves with longer wavelengths. They hope to hear the slow bass notes of the universe, created by supermassive black holes billions of times heavier than our Sun. They also hope to detect ancient waves that came from the violent expansion of the cosmos right after the Big Bang. Those primordial waves would have crossed the universe for more than 13 billion years. If they exist, they might contain a fingerprint of quantum gravity, a pattern hinting at the tiny constituents of reality. Imagine that, a signal older than every galaxy, a wave that remembers the birth cry of space-time. If detected, humanity would finally have a direct clue about what existed before there was space to expand into, and before time began to flow the way we experience it. But as we search deeper, we must remain skeptical and disciplined. Some theories predict that space-time is a smooth continuum forever. Others propose that it is made of discrete pieces like a giant puzzle. Still others suggest that geometry emerges from something non-geometric, like a vast network of quantum entanglement. In such a picture, space would not be built from tiny chunks of distance. Instead, connections between quantum states would create the illusion of location and direction. If those connections weaken, space stretches. If they strengthen, space contracts. In that view, gravitational waves might not be vibrations of geometry, but disturbances in the pattern of entanglement itself. A change in how information is shared between distant regions of the cosmos. This idea is bold and strange. It suggests that space-time might be an expression of something even deeper, something not located anywhere, something that does not look like space or time. It would mean that the universe does not sit inside space-time. Instead, space-time sits inside the universe information. That flips our understanding inside out. We usually think of information as something that travels through space. But if geometry emerges from information, then information is more fundamental than distance. Every location would be defined by the relationships that information creates. We stand in a confusing but revolutionary era of physics. Each new interpretation attempts to explain what space-time waves might truly be, yet none has been confirmed. None has been disproven. We possess powerful equations and precise tools, but we are still beginners in deciphering reality's deepest structure. What we can say with confidence is that space-time is not a silent vacuum. It is flexible. It reacts to mass and motion. It can store energy and release it in waves. It evolves. Nothing about it is rigid or permanent. Even the passage of time is not absolute. Time can slow near strong gravity. It can stretch with the expansion of the universe. It might even emerge from entropy, the natural tendency toward disorder. In that interpretation, time is simply the measure of how information spreads. The universe gradually learns more about itself, and that flow of knowledge is what we feel as the ticking of moments. Space-time is therefore not a container. It is a participant. It takes part in every event. It shapes and is shaped. It holds the stories of stars and planets and living beings. It carries echoes of ancient cataclysms. And perhaps gravitational waves are the syllables of the language it speaks. If we learn that language, we might discover that the emptiness around us is actually a vast and intricate structure, humming with hidden motion. Look up at the night sky once more. The silence you see is a deception. The universe is always moving, always vibrating, always rewriting its own geometry. You are inside a living cosmos, sailing on a sea of space-time that never rests. The search to understand its deepest origin has only begun. We know enough to be amazed. We know too little to be satisfied. The next chapters of this quest will take us into the heart of quantum gravity, into theories that challenge every old assumption, into experiments that stretch our technological ability to its edge. The answers may lead us to the smallest building blocks of existence, or to a realization that there are no blocks at all. There might only be relationships, ripples, and change. Space-time is the most beautiful puzzle ever created, and now that we can listen to its waves, we finally have a chance to solve it. There are moments in science that feel like the universe itself decides to speak. The year was 2015 when we first heard space-time whisper. It was not a loud shout or a cosmic explosion that shook observatories. It was a tiny change, a stretching and squeezing of distance far smaller than a single proton. Yet that faint tremor carried a message that traveled across more than 1 billion light-years. Two black holes, each heavier than many suns combined, spiraled into one another and merged. Their final spin and collapse sent a wave through the cosmos. That wave arrived on Earth as a subtle alteration in the geometry beneath our feet, invisible, yet detectable with the right kind of patience and precision. This was the first direct detection of gravitational waves. Predicted almost 1 century earlier by Einstein, they finally revealed themselves in the 21st century. Since then, more signals have poured in. Mergers of massive stars, collisions of neutron stars, cataclysmic dances of objects so dense that their gravity twists light and time beyond recognition. Each wave is a story. Each oscillation is a line of a cosmic diary written in the language of geometry. What are these waves exactly? They are not vibrations of a material substance. They are not like ripples on water or strings plucked to make music. Those familiar waves need matter to move. A pond needs molecules. A string needs tension. Gravitational waves need nothing but the universe itself. They travel through the vacuum, carried by the shifting shape of space-time. They are the purest message nature can send. They do not scatter off dust or gas. They do not fade as easily as light. They slice through matter and emerge unchanged, as if matter does not exist to them at all. Einstein mathematics showed that whenever mass accelerates, the curvature of spacetime changes. If the acceleration is gentle, the change remains local and calm. But if enormous masses move with violent speed, spacetime reacts dramatically. The changes propagate outward like ripples on a pond, except the pond is the universe, and the ripples are the geometry itself adjusting to the motions of colossal objects. Imagine a giant trampoline with metal spheres on it. When one sphere moves quickly and collides with another, waves spread across the surface. Now erase the trampoline. Keep the spheres. Let the waves travel through emptiness. That is closer to what gravitational waves truly are. They need no platform because the platform is the vibration. For most of human history, we assumed the universe was silent. Stars burned, galaxies rotated, but nothing seemed to make space-time itself vibrate. Such a concept felt abstract and unreachable. It took decades of theory to show the waves should exist. It took decades more to build machines sensitive enough to detect them. The Laser Interferometer. Gravitational wave observatory, called LIGO, stretches across kilometers. It uses laser beams and mirrors suspended so carefully that the smallest motion can be detected. When a wave arrives, it stretches one arm of the detector while squeezing the other. The mirrors shift ever so slightly. The beams reveal the shift, and humans hear the song of geometry. The first signal lasted only a fraction of a second, a quick rising chirp. But that short whisper contained a wealth of information. It revealed the mass of the black holes. It revealed how fast they spun. It revealed the final moment when they became one. And it proved that space-time is active, responsive, capable of ringing like a bell struck by invisible hammers made of pure gravity. From that moment, a new way of seeing the universe began. Astronomy no longer depends only on light. We can now observe the cosmos through its vibrations. Light waves show us surfaces. Gravitational waves show us depths. Colliding black holes cannot emit ordinary light because light cannot escape their gravity. But they can send out gravitational waves freely. These waves are windows into dark places where even photons cannot go. This discovery expands our senses. It transforms our understanding of what an observation can be. Human beings have evolved eyes to detect light and ears to detect pressure in air. But our instruments have evolved into something more astonishing. They are ears for the universe entire. They listen to the tremble of space-time like a stethoscope pressed against the chest of existence. Every new detection pushes our imagination. We hear the universe change shape. We learn how matter behaves when crushed into extreme density. We test Einstein theory in situations so violent that no laboratory experiment could ever approach them. So far, his equations survive every test, but that could change. When waves from deeper, older, more exotic events reach us, they might carry small deviations. Little clues that the smooth geometry Einstein imagined is only an approximation, a large-scale illusion cast by a more granular truth beneath. Gravitational waves also reveal how connected everything is. A disturbance in one distant corner of the cosmos eventually affects us here. The universe might be vast, but it is also unified. Space-time ties everything together. Pull one thread and the whole tapestry shivers. Why does space-time allow these waves at all? Why should geometry behave like something elastic, able to stretch and relax? There must be something that gives it that flexibility, something about its structure that allows disturbance to propagate. If it were truly rigid and unbreakable, no wave could ever form. If it were loose and fragile, waves would not travel smoothly for billions of years. The ability to vibrate might reveal that space-time is neither rigid nor fragile. It is something more like a perfectly tuned balance between stability and motion. This balance hints at possibility. If something can vibrate, it might have normal modes of oscillation, characteristic notes, frequencies that reveal its internal makeup. Physicists hope that one day, instead of listening only to the dramatic blasts of merging black holes, we will detect gentle hums, the natural ringing of space-time itself. Those hums might represent the fundamental musical notes of the cosmos, each note a clue to the smallest architecture that supports everything. Einstein did not believe in quantum randomness. He once wrote that God does not play dice, yet his own theory now pushes us toward a deeper mystery. If space-time vibrates, something deeper might be shaking, something that does not appear continuous or predictable, something that blends the smooth curves of Einstein geometry with the jittery probabilities of quantum mechanics. We stand in awe of what has already been heard, and yet, this is only the beginning. The universe has been singing since its birth. Humanity has only just learned how to listen. When a gravitational wave passes through you, it changes the distances between atoms in your body. You do not feel this change because it is so incredibly small. Even the strongest waves we have detected stretch space-time by only a tiny fraction of a proton width across a length of several kilometers. Yet this tiny change carries unimaginable energy. The black hole collision that produced the first measured wave converted several suns' worth of mass into pure gravitational radiation in less than a second. That power raced outward in all directions through the universe. The Earth happened to be in its path, and with the right instruments, we finally noticed. This moment changes how we think about the cosmos. In our everyday lives, gravity feels weak. You can lift a book with your fingers and easily overcome the pull of the entire planet. But this weakness is deceptive. Gravity controls the architecture of the universe. It shapes galaxies. It ignites the birth of stars. It decides when stars die and collapse. When gravity becomes extreme, its waves roar across the cosmos with tremendous strength. The fact that these waves barely disturb us here is a reminder of how enormous the universe is, and how far we are from the violence that creates them. As more detections arrive, we begin to map a universe invisible to traditional telescopes. We now know that black holes of many different sizes exist. Some only a few times heavier than our Sun, others millions or billions of times heavier. Some live in pairs, some spin rapidly near the speed of light. Some merge in spectacular unions that send space-time into a frenzy of motion. Gravitational waves reveal not only the density of these objects, but also the elegance with which they dance. The waves from merging neutron stars were especially revealing. Neutron stars are the densest known objects that are not black holes. Just 1 teaspoon of their material would weigh as much as a mountain on Earth. When 2 neutron stars spiraled together, the gravitational wave signal arrived first. Then, shortly after, telescopes around the world captured light from the explosion. We witnessed a cosmic forge where heavy elements like gold and platinum were created. The jewelry humans treasure owes its existence to catastrophic stellar collisions that shook the cosmos. This connection between gravity and matter gives us a sense of unity. Everything we see was shaped by events far beyond our sight. The gold ring someone wears might contain atoms born in a neutron star merger long before the Earth existed. The wave of gravity from that same ancient event may still be traveling outward, carrying a memory of how space-time responded to unimaginable pressures. Every ripple that reaches us is a form of communication. The universe does not waste information. It delivers signals from events that light alone could never reveal. Some black hole collisions remain completely dark. They swallow light so efficiently that not even the brightest explosion escapes. Yet their gravitational waves betray their presence. They cannot remain silent forever. The geometry around them cries out with every twist and turn. This new form of astronomy also tests the most fundamental laws we know. Light always travels at the speed of light. But do gravitational waves always move at exactly the same speed? So far, yes. Measurements have shown that they race through the universe at the same ultimate limit that photons obey. This confirms Einstein's work in a dramatic and unexpected way. Any difference, however tiny, would have exposed flaws in our current picture. But nature remains consistent, at least at the level we can measure today. Still, mysteries remain. Gravitational waves have no mass, at least according to general relativity. But if they have tiny mass in a deeper theory, they would not travel exactly like light. They might change speed depending on frequency. They might fade or distort as they propagate. The wave data collected so far is too young and too sparse to reveal such subtle clues. But the universe has plenty of time. More events will come, stronger ones, older ones, waves traveling from farther back in cosmic history. There is also the question of polarization. Light waves can twist in different directions. Gravitational waves can too, but in ways more complex because they stretch and squeeze space itself. If space-time has an atomic structure, the way it distorts under different wave directions could reveal imperfections or discrete patterns. It would be like noticing the grain in a piece of wood only when you slide your hand in just the right direction. To search for such effects, scientists analyze gravitational waves with exquisite care. They compare real signals against Einstein predictions. So far, the match is nearly perfect. But nearly perfect is not enough. The tiny differences that could expose the smallest structure of space-time might be buried beneath noise. We must build better detectors. We must listen longer. The next generation of observatories will be constructed deep underground. Others will float between spacecraft in the silence of space itself. They will measure wavelengths far longer and far shorter than anything we detect today. They will hear the universe as it hums rather than shouts. And when that hum is fully understood, we might discover that space-time has its own resonant frequencies. A cosmic-scale musical instrument whose deepest notes carry secrets from before the first galaxy ignited. The presence of gravitational waves tells us that the universe is not static. It changes, it responds, it transforms. Even empty space can be excited. Even nothingness can vibrate. That is not a familiar kind of nothing. It suggests that what we call emptiness is full of latent possibility, a field capable of motion and tension and release, a realm where geometry itself is a dynamic player in the drama of creation and destruction. When Einstein finished his theory of general relativity, he believed gravitational waves might be too weak ever to detect. He was wrong, though not about the weakness. Instead, he underestimated human ingenuity. We have learned to measure the tiniest tremors in reality. The universe spoke softly. We built a way to hear. And now the question grows urgent. If space-time can vibrate, what is the ultimate source of that elasticity? Why does the universe ring? Gravitational waves do not only reveal violent collisions, they also reveal how space behaves on its own. Imagine the universe as a vast ocean. When a ship crashes through the water, big waves form. But even on a calm day, the ocean is never perfectly still. Tiny ripples glide quietly across the surface. In space-time, these quiet ripples might exist everywhere. They might be created by the gentle shifting of matter in distant galaxies, or by the natural resonances of the cosmos itself. If we learn to detect those softer murmurs, we could uncover the everyday behavior of space-time, not only its dramatic outbursts. There is a deeper question beneath all of this, a question that rises like an unavoidable tide. Why can space-time ripple at all? What gives it the ability to deform and relax? Something must grant the universe flexibility. Something must allow it to store energy within its shape and then release that energy as a traveling disturbance. If space-time were truly empty, without any kind of structure, how could it support waves? The answer might lie in the unity of matter and geometry. According to Einstein, mass and energy tell space-time how to curve. But the reverse is also true. Curved space-time tells mass and energy how to move. The universe behaves as if geometry and matter are parts of the same thing. Not separate, not independent. If matter changes, geometry responds. If geometry changes, matter reacts. They are bound in a perfect feedback loop. So imagine taking matter to its extreme expression, a black hole. There, gravity is so strong that light itself cannot escape. Inside that region, space-time falls inward relentlessly. Distances collapse. Time slows. And yet even in that ultimate grip of gravity, black holes can vibrate. After they merge, the single black hole created from the collision rings like a struck bell. The pitch of that ring tells the mass and spin of the final object. The ring fades as the black hole settles into stability. Gravity waves carry the fading tone outward. It is astonishing that something with no surface, no atoms, and no physical material can ring. The ringing suggests that the shape of space-time has resilience. It resists being deformed and then rebounds. That behavior seems like the property of something with internal structure. Some physicists argue that gravitational waves are like phonons in a solid. A phonon is a vibration of a crystal lattice, a wave of sound moving through the orderly arrangement of atoms. If space-time were made of tiny interconnected units arranged in a vast network, perhaps gravitational, waves are the vibrations of that network. Tiny disturbances traveling from node to node. In that case, the structure beneath space-time would not look like a surface or a foam or any familiar material. It would be a network of relationships, pure information, woven into geometric form. If that is true, then the strength of gravity would emerge from how strongly those nodes connect. The stretching of distance would be the stretching of those connections. Time would be the flow of information along them. Energy would be the cost of altering those relationships. And gravitational waves would be the universe shifting its pattern of connection as massive events realign the structure. It is a breathtaking possibility that the universe is not a thing, but an ongoing calculation. Not a stage, but a process. Not matter, floating in a void, but patterns of information that give rise to matter and void. In that view, Einstein theory describes the large-scale shape of relationships. Quantum theory describes their smallest unpredictable flicker. The two may be opposite sides of a single truth. A truth that says geometry is not fundamental. Relationship is fundamental. Yet we must be honest. We do not know. The data is not sufficient. The theory is not complete. We are explorers in a darkness still too thick to pierce. Gravitational waves give us our first sense of motion in that dark. Our first hint that beneath the smooth cloak of general relativity lies something else. Something we are straining to see. The challenge now is precision. We have heard the loudest and clearest waves. The universe is capable of producing infinitely more subtle ones. Those subtle waves might arrive continuously from millions of sources. They might blend into a background hum, a steady vibration that surrounds us always. If detected, that hum could reveal whether space-time is smooth or grainy. It could show whether there are favored directions or tiny imperfections. It could test whether time and space break into indivisible chunks when you zoom in close enough. Detecting this background is like trying to hear a faint murmur in a noisy room. We must learn to quiet the noise. We must build instruments far more sensitive than anything existing today. We must spread detectors across continents. We must place others in space to escape the shaking of Earth's own surface. The more accurately we measure, the more clearly the universe will speak. There is another frontier, waves from the beginning of time. The universe started hot and dense. It expanded rapidly in a burst called inflation. That expansion stretched tiny quantum fluctuations into cosmic scales. It should have created gravitational waves that still travel through the universe today. They would be older than stars, older than galaxies. They would carry direct evidence of how space-time behaved when everything was crammed into a point smaller than an atom. Those ancient waves, if found, would be the ultimate clue. Proof that space-time has a quantum origin. The search is ongoing. Instruments watch the sky for delicate patterns in the ancient light of the cosmos. If gravitational waves from the first fraction of a second exist, They will leave subtle twists in the cosmic microwave background. Detect those twists, and we decode the handwriting of creation. The journey has only just begun. Gravitational wave astronomy is less than a decade old, yet already it has transformed our understanding. It shows that the universe is not quiet. It is alive with motion and sound. If we continue listening, we might learn that space-time is more than geometry. It might be a dynamic entity that grows, ripples, communicates, and perhaps even computes. The universe vibrates because everything within it is connected. Motion anywhere means motion everywhere. Space and time are not the silent void we once imagined. They are the medium through which the story of the cosmos is told. Every wave is a sentence, every ripple a voice. We are learning to understand the language. And the greatest discovery may come not from what these waves reveal about black holes or stars, but what they reveal about the structure that holds everything together. The secret threads of reality may finally come into focus as we listen more closely. Einstein's genius reshaped our understanding of gravity and the structure of the universe. He showed that space and time form a single continuum. He showed that mass and energy bend that continuum. He showed that gravity is geometry in motion. Yet there was one mystery he could not solve. He could not unite his beautiful continuous space-time with the strange and grainy world of the quantum. Quantum mechanics arrived almost at the same time as general relativity, yet the two theories speak different languages. Quantum mechanics tells us that energy comes in packets. It tells us that motion is uncertain until it is observed. It tells us that the smallest scales of nature flicker with randomness. Particles pop in and out of existence. Forces are exchanged through messengers called quanta. Nothing is smooth. Nothing is fully predictable. General relativity, in contrast, describes the universe as if it were a perfect sculpture. Smooth curves, predictable motion, no uncertainty at all. According to Einstein equations, if you know the mass and energy in a region, you can calculate the geometry exactly. The curvature tells matter how to move with no guesswork. It seems like a flawless clockwork cosmos. These two pillars of physics both work astonishingly well. They explain everything from the tiniest particles to the largest galaxies. But they do not agree about what reality is made of. One says the universe is continuous. The other says the universe is discrete. One says events unfold with certainty. The other says uncertainty is fundamental. The conflict becomes undeniable in the most extreme environments. In the center of a black hole, the geometry becomes so curved that the math of general relativity breaks down. In the first moments after the Big Bang, densities become so high that relativity predicts infinities. Infinite curvature, infinite energy. Those infinities are nature refusing to answer. They tell us we have reached the limit of the smooth picture. At the tiniest scale imaginable, the Planck length, the conflict becomes unavoidable. That length is about 1 decimal point, followed by 35 zeros of a meter. If you try to measure something smaller, the energy required becomes so great that you would create a tiny black hole and lose the information entirely. At that scale, time itself also becomes uncertain. The universe stops allowing sharp definitions. The smooth tapestry of space-time appears to unravel. Einstein spent decades trying to find a way forward. He believed there must be a deeper theory that explains both geometry and quantum behavior. He believed nature must be unified, but he never found the answer. The quantum world bothered him. Its uncertainty felt like a flaw in logic. He once said that he could not believe the universe was governed by chance. Yet every experiment shows that quantum randomness is real. The puzzle remains unsolved. Physicists today believe that the only way to fully understand gravity is to make it quantum. If matter obeys quantum rules, and if gravity reacts to matter, then gravity cannot remain purely classical. It too must have quanta. The wave nature of space-time must be built from tiny steps, just as the wave nature of light is built from photons. Those hypothetical quanta of gravity are called gravitons. If they exist, then gravitational waves are not smooth ripples, but vast ensembles of these tiny quanta moving in harmony. But detecting a single graviton is almost impossible. Gravity is incredibly weak compared to the other forces. A magnet on a refrigerator can hold up a piece of metal against the pull of the entire Earth. That weakness means that the interaction between gravitons and matter is tiny. To detect a graviton directly, you would need a detector so sensitive that it would collapse into a black hole under its own weight. Nature hides the quantum of gravity behind a wall of scale. There is another clue that the smooth picture must fail. The vacuum of space is not empty. Quantum theory says that fields fill every point of space, even when no particles are present. Those fields fluctuate constantly. They create energy out of nothing, and then take it back before anyone can measure it. These vacuum fluctuations should tug at spacetime and curve it. Yet the amount of curvature we see in the universe is unbelievably small compared to what the quantum vacuum predicts. This is called the cosmological constant problem. It is one of the most troubling disagreements between the two great theories. Another sign of the conflict appears in black holes. According to relativity, nothing escapes a black hole. But quantum mechanics says that pairs of particles pop out of the vacuum everywhere, even near the event horizon. If one of those particles falls into the black hole and the other escapes, the black hole slowly loses mass. It evaporates. Stephen Hawking showed that this evaporation must happen. But if the black hole disappears entirely, where does the information it once contained go? Quantum mechanics says information cannot be destroyed. General relativity says the information vanishes. Both cannot be right. These problems are not mathematical inconveniences. They are alarms. They warn us that our understanding of gravity and space-time is incomplete. The universe is demanding a new theory that replaces the divided picture with one unified vision. A theory where space-time is not infinitely smooth. A theory where geometry obeys quantum rules. And this brings us back to gravitational waves. These waves are ripples in space-time. If space-time has atoms, the ripples must reveal them. If geometry is made of quanta, the waves will show hints of that discreteness when measured with rising precision. Every new detection is a chance to test whether the universe is smooth or constructed from something finer. Einstein gave us a map of the cosmos that works almost everywhere. Quantum mechanics gives us a map that works almost everywhere else. Now, we stand in the narrow territory where both maps fail. The Planck scale, the heart of black holes, the first instant of time. In those places, space-time must be rebuilt from the ground up. The universe has sent us clues in the form of gravitational waves. They are the vibrations of the very thing we are trying to understand. They could reveal what lies beneath the smooth illusion. They might show that space-time is a product of some deeper quantum structure, or they might prove that geometry is fundamental after all. Either way, the search promises the greatest discovery in the history of physics, a united picture of the cosmos from smallest to largest, a world where time, space, matter, and information are all expressions of a single underlying reality. Quantum mechanics and general relativity do not only disagree in abstract equations, they clash in very real physical situations. Imagine an object being pulled into a black hole. From far away, time appears to slow for the falling object. It seems to freeze near the event horizon. But according to its own clock, time flows normally as it plunges inward. The geometry of space-time stretches time differently depending on gravity. This is Einstein vision. Now add quantum mechanics. The vacuum near the event horizon is full of flickering energy. Particle pairs appear and vanish constantly. One sometimes escapes while the other falls in. That escape creates what is known as Hawking radiation. The black hole slowly evaporates. But if that evaporation completes, everything that fell in might vanish without a trace. Quantum mechanics screams that information cannot be lost. The contradiction becomes unavoidable. Physicists have debated this puzzle for decades. They propose wildly different solutions. Some ideas say that the horizon stores information like a memory surface. Some say the black hole interior is replaced by a complex quantum structure. Some argue that geometry itself becomes fuzzy and changes in a way we cannot yet describe. All of these ideas imply that spacetime must obey quantum behavior at its core. The smooth continuum cannot be the ultimate truth. There is also the mystery of energy. In a quantum vacuum field, the energy fluctuates everywhere. If you add up all those fluctuations across the entire cosmos, the amount of energy should be unbelievably huge. It should curve spacetime so strongly that the universe would either tear apart instantly or collapse into its own gravity. Yet the observed curvature is tiny. Something must cancel almost all of that vacuum energy, or something must change the way geometry responds. Either way, the simple picture of smooth spacetime does not survive. These conflicts show that Einstein left behind the hardest unsolved problem in physics. He did not fail. He reached a wall that no one has yet climbed. The wall between the continuous and the discrete, between certainty and uncertainty, between geometry and probability. The wall is the Planck scale, smaller than any particle, faster than any time we can measure. In that territory, the mathematics of general relativity produces infinities. The mathematics of quantum mechanics produces contradictions. Nature is quietly telling us that our tools are incomplete. To move forward, physicists must imagine something entirely new. They must build a theory where space-time is not the background, but the outcome. They must show how geometry emerges from quantum ingredients. They must explain how information survives even in the heart of a black hole. They must describe how time begins and why it only moves in one direction. These questions are not merely philosophical, they are testable. Gravitational waves are one of the tests. Every wave that arrives is a chance to examine how space-time behaves under extreme pressure, a chance to see whether the wavefront begins to distort at tiny scales, a chance to find clues that the continuous approximation starts to break. If the wave behaves exactly as Einstein theory predicts, down to the finest detail, that would suggest space-time is truly smooth. But if we detect even one anomaly, one deviation from the prediction, that could reveal the first glimpse of a deeper quantum theory. Quantum mechanics offers another hint that space-time might emerge from something else: the concept of entanglement. When two particles interact, they can become linked in such a way that measuring one instantly affects the other, no matter the distance between them. This connection ignores the usual concept of space. It seems that information can leap without crossing any distance at all. That suggests distance itself might not be fundamental. It might be an illusion created by deeper relationships. Perhaps the universe is not a grid of points stitched together. Perhaps it is a web of entangled states. When those states are strongly connected, the geometry appears close. When they are weakly connected, the geometry appears far. In that picture, space-time is not something objects live in. Space-time is a map of how strongly they share information. If those connections shift, waves of geometry would ripple outward, and we would call them gravitational waves. To understand this idea, imagine a network of people holding hands in a dark room. The pattern of who holds whose hand creates a shape. If they change the pattern, the shape changes. Now remove the people and the hands. Replace them with quantum information. That network forms geometry. If the connections change rapidly, the geometry vibrates. Waves travel through the pattern. That motion feels like gravity. This might sound abstract, yet it is one of the most promising paths forward. It connects the uncertainty of quantum mechanics with the curvature of relativity. It explains why space can expand without requiring more substance. It explains why time flows like a river instead of remaining static. Time might simply be the universe updating its information. Gravity might simply be the cost of maintaining the structure of that information. Still, we must not leap to conclusions. Every theory must face experiment. We cannot assume the universe works this way just because the mathematics is beautiful. Gravitational waves are becoming our best chance to test these ideas. If space-time is woven from quantum relationships, the waves might eventually show tiny distortions that reveal that weave. They might show that Einstein model is only the smooth surface of something granular below, like the calm appearance of a beach hiding millions of grains of sand. But perhaps the greatest conflict of all is the nature of time. In relativity, time is simply another dimension. It can stretch and bend. It can slow near strong gravity. The past and future become coordinates. But in quantum mechanics, time is absolute, a stage on which probabilities evolve. Neither theory explains why time only moves forward, why we remember the past but not the future, why the universe began in a low entropy state and continues drifting toward higher entropy. Time itself might emerge from quantum behavior, not from geometry. And gravitational waves might help us show how. We are confronting the most profound puzzle ever conceived. We know enough to see the conflict. We know too little to solve it. Einstein left a question hanging in the air. What is space-time really? Is it a smooth field, a quantum network, something else entirely? Until we answer that, every description of the universe remains incomplete. The clash between relativity and quantum mechanics is not a flaw in physics. It is a doorway leading to the next revolution in our understanding of reality. Gravitational waves might be the key that unlocks it. The tension between the smooth and the grainy shows itself in another remarkable way. According to general relativity, space-time can be stretched continuously without limit. During the first moments of the cosmos, space-time expanded at an unbelievable rate. Regions that were once smaller than an atom were pulled apart until they became larger than entire galaxies. Yet quantum mechanics teaches that distances cannot be measured with infinite precision. There must be a smallest meaningful unit. If so, the expansion of space must involve something new appearing. New points of geometry must be created. But how does the universe create space? What mechanism builds more of the very stage on which existence unfolds? If space-time is made of discrete pieces, then the expansion of the universe is the creation of new pieces. If it is continuous, the expansion is simply stretching an already infinite fabric. Both explanations raise mysteries. A continuous fabric has no smallest scale. It can always be stretched thinner. But that clashes with the graininess of quantum mechanics. A discrete structure must have rules that govern how new units are added. Those rules might reveal themselves in the pattern of gravitational waves that travel through expanding space. Subtle effects could appear as waves move across regions where new space-time units are being created. These effects are faint, but not impossible to detect with future instruments. The idea that space-time might be built from something deeper has already inspired many approaches to quantum gravity. Loop quantum gravity proposes that space-time is woven from loops of quantized geometry. String theory proposes that the smallest entities are tiny vibrating strings whose different notes create particles and forces. Other theories suggest that space emerges from quantum entanglement. Some imagine that space-time is a hologram, a projection of information stored on cosmic boundaries. All of these ideas try to solve the same conflict. All struggle to match the perfection of Einstein equations where they have been tested. None has delivered a complete picture that unites every observation. Even the simplest question remains unanswered. What happens at the center of a black hole? Does space-time end? Does it continue, but in a form we cannot recognize? Does the information that falls in remain encoded in the geometry? If so, how does it escape when the black hole evaporates? These questions are not side issues. They are the heart of the struggle to unite the quantum and the geometric. We know that the smooth surface of space-time is fragile. It works well when gravity is gentle and scales are large. But the universe contains places where gravity rips through the calm. There are moments when time nearly stops and distances shrink to nothing. At those edges of understanding, our confidence in the smooth picture dissolves. We can pretend the equations remain valid, but the infinities they produce are warnings. The map no longer describes the territory. Quantum mechanics is no easier. It refuses to respect geometry as a definite backdrop. Particles exist as probabilities until measured. They tunnel through walls. They entangle across vast distances. They break the classical idea that information must travel through space. These behaviors tell us that space and distance are not as fundamental as we assume. Location might be an emergent property. Time might be emergent too. If observables depend on interactions rather than absolute positions, then spacetime might be a consequence of quantum rules, not a framework that exists first. The search for quantum gravity is not simply about solving equations. It is about uncovering the foundation on which reality is built. Everything we know depends on spacetime. Every object, every force, every thought. If spacetime is a secondary effect, what then is primary? What is the substance of existence when you remove position and duration? Something must remain, something that gives rise to the illusions of here and there, before and after. Gravitational waves are gifts from the universe that challenge us to answer. They show that geometry behaves dynamically. They reveal that spacetime can carry energy and change shape. They prove that the universe is not a static container, but a system in motion. If we examine those waves closely enough, we might see tremors of the quantum beneath the classical calm. The ripples may carry hints that geometry comes in packets. They may show that the propagation of gravity is affected by microscopic structure. Those hints would be tiny distortions, minute delays or frequency shifts, patterns that refuse to match a perfectly smooth theory. To find such clues, we must measure the behavior of spacetime with unimaginable accuracy. We must compare waves from different parts of the cosmos. We must catch distortions as they accumulate over billions of years. We must listen to the universe with both patience and sophistication. The challenge is steep. The reward would be a revolution. Consider this. If spacetime is built from a quantum network, then the merging of black holes should do more than send out waves. It should alter the structure of the network itself. The reconnection of quantum links could leave a faint signature, a scrambling of information that takes time to settle. That delay might be visible in the ring-down phase of a gravitational wave, the part of the signal where the black hole relaxes into stability. If we see tiny echoes in those ring-downs, repeating patterns that should not exist, that could be evidence of a deeper interior structure. Physicists search for such echoes now. So far, nothing definite. But the quest continues. Quantum theory also suggests that spacetime might not be perfectly smooth even in calm places. There could be random jitter at the smallest scale. Tiny fluctuations of distance and time. Gravitational waves passing through such jitter might become slightly fuzzy. Their perfect shapes could acquire tiny imperfections. These imperfections would reveal the size of the quantum structure. They would reveal the frequency at which smooth geometry gives way to discrete quanta. No experiment has seen these effects yet, but our tools improve. Every year of observation adds data. Every new instrument sharpens our ear. One day, perhaps sooner than we expect, a wave will arrive with just the right clarity to expose something new. A fracture in the smooth surface. A sign that reality is granular. A hint that Einstein's view, though magnificent, is only part of the story. When that happens, it will not diminish Einstein. It will complete him. His theory is an approximation of a truth, even deeper than he imagined. He suspected this. He spent his later years searching for a unified description. He believed that nature could not remain divided. He trusted that the underlying structure of the cosmos is elegant and complete. We stand now where he once stood, with a beautiful theory that cannot be the final word, with a mystery that refuses to be ignored, with a universe that sends us ripples of its hidden architecture. The quest to unify the quantum and the geometric is the central challenge of modern physics. Solving it will illuminate every corner of existence. And as we listen to gravitational waves, we draw closer to that illumination. Space-time is not silent. It sings of a deeper truth, a truth waiting to be understood. If the universe has a smallest structure, then everything we see is built from something more basic. Not atoms of matter, atoms of space-time. Pieces of geometry that cannot be divided further. For more than 1 century, physicists have been searching for those pieces, trying to discover whether the smoothness of Einstein geometry is only a grand illusion. The search has led to bold ideas that stretch the boundaries of mathematics and imagination. The first clue that space-time might be made of smaller ingredients comes from its behavior. It bends, it stretches, it ripples. In our experience, things that can bend and ripple are usually made of parts. A guitar string vibrates because countless atoms pull and push on one another. A wave travels through water because molecules transfer motion. What if gravitational waves are like that? What if they are vibrations of a deeper lattice we cannot yet see? Some physicists believe the answer lies in loops. Loop quantum gravity proposes that space-time is woven from tiny closed lines of energy. These loops join together in intricate webs called spin networks. Each intersection defines a quantum of volume. Each connection defines a quantum of area. There are no smooth surfaces in this picture. Geometry comes in building blocks. Space is quantized the same way energy is quantized in atoms. When you zoom in far enough, you would not see a fabric. You would see a network of nodes connected by links, each carrying a spin that determines the shape of the universe at that point. If loop quantum gravity is correct, then distances cannot shrink smoothly to zero. They stop at the Planck length. Areas and volumes have smallest possible values. Inside a black hole, the singularity predicted by general relativity would not exist. The geometry would reach its minimum and bounce. The collapse would reverse. Space would not tear. It would heal itself. This approach also suggests that the Big Bang was not the beginning. It was a bounce from a previous contraction. If that is true, then the universe might be eternal, cycling through ages of collapse and rebirth. Another idea begins not with loops, but with strings. String theory proposes that the fundamental objects are tiny strands of energy that vibrate like miniature violins. Different vibrations create the different particles of nature. One type of vibration acts like a photon, another acts like a graviton. If strings exist, then gravity would automatically have quantum properties. Space-time would not be fundamental. It would emerge from the interactions of strings. But strings require extra dimensions curled so tightly that we cannot detect them. These hidden dimensions could be smaller than the smallest particle, rolled into complex shapes that determine the forces of the universe. String theory also introduces the idea of branes, surfaces of many dimensions on which strings attach. Our universe might be one of these branes floating in a higher dimensional space. Gravity might leak into those extra dimensions, making it appear weak in ours. Gravitational waves might one day reveal evidence of those hidden spaces. If a wave arrives slightly altered or missing part of its signal, it could mean that some of its motion escaped into higher dimensions. There is yet another possibility. Space-time might not be a material at all. It might emerge from pure information. Quantum entanglement could be the glue that builds geometry. If two regions of the universe share strong entanglement, then they appear close in space. If their entanglement fades, they drift apart. This idea transforms distance from a physical separation into a measure of shared information. Gravity would arise from changes in that information. When mass enters a region, it alters the pattern of entanglement. The geometry updates. A ripple spreads outward, and we call that ripple a gravitational wave. This information-based view solves several puzzles. It explains why black holes have entropy. It explains why their surface area, not their volume, determines the amount of information they contain. It connects gravity with thermodynamics and computation. The universe begins to look less like an object and more like an algorithm running on an unimaginable quantum processor. There is also a theory that space-time behaves like a fluid. If you zoom in enough, maybe you would not see fixed nodes or strings, but instead, a swirling quantum liquid. The smooth geometry we observe would be like the calm surface of a deep ocean. Gravitational waves would be pressure waves in that fluid. Singularities would be places where the fluid churns violently rather than points of infinite density. The equations of general relativity would be like the large-scale behavior of water, not a description of the molecules themselves. Each theory paints a different picture of the unseen. Each has strengths and weaknesses. None has been proven correct. The universe keeps its smallest structure hidden behind the veil of the Planck scale. Our technology cannot yet reach that far, but gravitational waves might bring that scale to us. Every wave travels enormous distances. Small effects accumulate. If space-time is discrete, waves might scatter slightly. They might lose coherence. They might reveal anisotropies that should not exist in a perfectly smooth continuum. Physicists search gravitational wave signals for unexpected quirks, tiny deviations in timing, subtle distortions in shape, patterns that betray the presence of an underlying grid. Some experiments also search for noise that does not come from the Earth or from detectors, but from space-time itself. A kind of jitter that comes from the universe's smallest steps. If found, that noise could reveal the size of the atoms of space-time. There is still another approach to this search. Instead of looking for new theories in mathematics alone, we look into the universe past. The earliest moments of existence would have created primordial gravitational waves, born from fluctuations in the newborn geometry. Those waves have traveled through billions of years, untouched by matter. They contain the signature of the original architecture. Detect them, and the curtains of ignorance may finally lift. The search is ambitious. It will take decades. It might require instruments in space stretching across millions of kilometers. It might require detectors cooled to near absolute zero to remove all thermal noise. But the reward is beyond measure. We would know how existence composes itself. We would know whether space is a fluid, a crystal, a network, a hologram, or something we have not yet imagined. If space-time has atoms, then the universe is far more than a smooth cosmic stage. It is an intricate machine. Every vibration carries the legacy of its construction, and gravitational waves may be the sound of that machinery in motion. The search for the smallest structure of space-time forces us to rethink our most familiar ideas. For centuries, space was seen as the container in which everything happens. Time was the universal clock that ticked forward the same for everyone. Then Einstein showed that both space and time are flexible. They stretch, they compress, they blend into one another. Now physicists wonder if the fabric that bends might itself be stitched together from something deeper. If so, the smoothness we experience would be like the smooth surface of a cloth viewed from afar. Only when magnified would the weave appear. Loop quantum gravity takes this metaphor literally. In this approach, the geometry of the universe is made from spin networks, webs of quantum threads. These threads come in smallest units. They do not allow infinite refinement. The threads intersect at nodes, forming a network that defines volume. When the network vibrates, gravitational waves move through it. Different vibrational patterns would correspond to different shapes of space-time. The astonishing suggestion is that emptiness is not truly empty. The vacuum is a kind of quantum scaffolding. String theory paints a picture that is at once more dynamic and more elusive. The tiny strings it proposes are unimaginably small. They are said to be about 1 decimal point followed by 34 zeros of a meter in length. They vibrate in multiple dimensions. Most of those dimensions are twisted so tightly that they remain hidden. Yet these curled dimensions might be responsible for the strength of forces and the mass of particles. Gravity in this picture is weaker because its vibrations do not remain confined to our familiar 3 dimensions. The graviton, the quantum of gravitational waves, would be a closed string able to wander into the higher dimensional space. Gravitational wave signals from cosmic events might show faint signs of this wandering if part of their energy disappears into the hidden realms. There are even more radical ideas. Some physicists imagine that space-time is similar to a quantum computer. The basic operations on the underlying qubits generate the illusion of geometry. Space appears because information patterns adopt a structure that mimics distance. Time appears because those patterns evolve. In this view, the universe does not exist in space. Space exists in the universe computations. Gravitational waves would be updates spreading through this quantum network. Their speed would reflect how quickly information can move in the underlying code. All of these perspectives share a common theme. Spacetime is not the final layer. It is the result of something more fundamental. Whether that something is loops, strings, information, or fluid-like quanta, the smoothness of geometry must emerge from microscopic behavior. Just as temperature emerges from the motion of molecules, curvature might emerge from the structure of spacetime atoms. There is a quiet elegance in this idea. It suggests that geometry is not a static backdrop, but a dynamic expression. Every region of spacetime would hold memories of interactions that shaped it. When a gravitational wave passes, those memories are jostled. When a black hole forms, the network rearranges. When the universe expands, new relationships are created. The cosmos becomes something alive, evolving its own architecture. But elegance alone is never enough in science. We need evidence. We need quantities that can be measured. One promising direction is to search for the smallest bit of area. Loop quantum gravity predicts that area is quantized, coming in multiples of a very small unit. If we examine the horizon of a black hole, which is a surface, its area should change only in discrete steps. When a black hole emits radiation and shrinks, its surface should shrink in multiples of that smallest quantum. Gravitational wave signals from black hole mergers might reveal this stepping if our detectors become precise enough. Another proposed test looks at the path of extremely high-energy particles. If spacetime has a grainy texture, particles moving at enormous energies might scatter slightly from its irregularities, arriving on Earth with tiny delays or distortions. Similar effects might influence gravitational waves directly. The perfect sweeping arc of a wave might warp very subtly as the wave encounters the hidden details of spacetime. This would appear as a barely noticeable shift in the frequency or arrival time compared to predictions. No such anomaly has been found yet, but the search has barely begun. There is a still more profound line of evidence waiting in the early universe. If the cosmos underwent rapid inflation in its first moments, quantum fluctuations would have been stretched across cosmic scales. Those stretched fluctuations would create primordial gravitational waves. These waves would be older than galaxies, older than stars, older than atoms. They would carry the signature of the small-scale structure from which the universe emerged. To find them, scientists study the cosmic microwave background, the oldest light we can see. If primordial waves exist, they will twist the polarization of that ancient radiation. Experiments around the world and in space are searching for that twist now. The importance of these searches cannot be overstated. If we discover the atoms of spacetime, we will rewrite physics from the ground up. We will know what the universe truly is at its smallest scale. We will know how to unify gravity with quantum mechanics. We will know what happened at the birth of everything. And if spacetime can be reduced to simpler parts, perhaps laws that seem mysterious today will appear natural. Gravity would no longer be an assumed force, but a consequence of structure. Time might no longer require special rules to flow. It would be what the universe does when its pieces interact. We stand at the edge of this understanding. Our tools are advancing. Our theories grow bolder. The universe continues to send us its messages in the form of gravitational waves. With every detection, we apply pressure to the smooth picture of space-time. One crack could reveal the network beneath. One anomaly could unveil the architecture of existence. To find the atoms of space-time is to uncover the foundation of reality. It would mean that what we call empty space is alive with hidden form, that the void is a labyrinth of connections, that the cosmos builds itself from microscopic steps, and gravitational waves are not mere ripples, but direct evidence that the foundation can move. The smallest structure may soon become visible not through microscopes, but through the largest events in the universe. When black holes collide, when stars collapse, when the cosmos vibrates, the ground of existence reveals its rhythm. Gravitational waves may someday become the most precise probes of the deep architecture of the universe. They do not merely move through space-time, they are changes in space-time itself. When a wave passes, nothing travels across the space. Instead, the distance between points alters. If those points are built from smaller components, then the wave must propagate through the structure that binds those components together. That interaction might reveal its shape. Imagine tapping on a wall. The sound you hear depends on what the wall is made of. Stone, wood, metal, each produces its own timbre. In the same way, the universe might have its own timbre. The tone of a gravitational wave might vary depending on the medium beneath. The universe might ring differently if space-time is built from loops rather than strings, or if it emerges from quantum entanglement. We are only beginning to listen closely enough to hear subtle shifts in that ringing. There is another powerful idea that unites many approaches: information. In every theory, where space-time is not fundamental, information becomes the real substance. Whether stored in loops, or encoded in strings, or woven into entanglement, the universe is built from data. Geometry is the arrangement of that data. Physics is the evolution of that data. Matter is a pattern within the data, and gravitational waves are the reorganizing of that data at the largest scales. This perspective helps resolve a long-standing mystery. Black holes have temperature and entropy. Entropy counts the number of microstates that correspond to a given macrostate. If a black hole has entropy, it must have microstates. That means the smooth horizon hides countless tiny degrees of freedom. Those degrees of freedom are the atoms of spacetime. When the area of the horizon changes, the number of these atoms changes. The entropy of a black hole grows and shrinks in direct proportion to its surface area. That relationship suggests something astonishing. Information about matter swallowed by a black hole is stored on its surface, not inside its volume. This idea echoes something even more astonishing: the holographic principle. The universe might be like a hologram where the information in a region of space is encoded on a lower dimensional boundary. Space-time inside is a projection of information on the outside. Gravitational waves interacting with horizons might provide our first chance to test this. The waves could disturb the microstructure and then reveal how it responds. The response could look different from what a smooth geometry would predict. This difference might appear as faint ripples trailing the main signal, like tiny echoes that should not exist if the horizon were a perfect classical surface. Physicists look for these echoes in real data. The signals remain unclear, but the search continues with growing sensitivity. Even if space-time has a fundamental structure, we may not find it easily. The universe is clever at hiding its secrets. The smoothness of space-time at human scales is so perfect that we may need to observe countless cosmic events to see even the slightest deviation. But we are persistent. Our detectors become quieter. Our algorithms become sharper. Our understanding deepens with every signal. We can imagine a future where gravitational wave observatories spread across the solar system, instruments floating far from Earth, tiny vibrations lost in terrestrial noise, space-based detectors stretching across millions of kilometers, quantum-enhanced sensors measuring distances with unimaginable precision. These future tools could reveal the faint whisper of space-time fabric. They could hear the murmurs of primordial waves from the dawn of existence. They could resolve the smallest tremors that hint at the atoms of geometry. The idea of atoms of space-time changes everything. It means the universe is not continuous. It means there is a smallest distance, a smallest area, a smallest volume. It means smooth curves are approximations, created by countless tiny steps. It means time moves forward in discrete ticks. It means the cosmos is a creation not of substance, but of structure. Throughout history, physics has repeatedly reduced complexity to simplicity. The solidity of matter became atoms. The diversity of atoms became smaller particles. The forces between those particles became quantum fields. Now we suspect that those fields themselves sit on a deeper foundation. The ultimate reduction may be spacetime itself. When we reach that level, we will know that the universe is built from information and connection, and that nothing exists without relationship. That realization changes how we see ourselves. We are not isolated objects floating in emptiness. We are expressions of the same fabric that shapes galaxies. We are vibrations of the same structure that carries gravitational waves across cosmic distances. The atoms that make us are built inside a geometry that itself might be built from finer elements. We are creatures of this architecture from top to bottom. To understand it is to understand our place in existence. Gravitational waves are not just a new kind of astronomy. They are a new way of asking what the universe is. Each detection is a conversation between human curiosity and cosmic truth. Each improvement in sensitivity lets us hear deeper, like moving from the roar of storms to the quiet breathing of the sea. We are learning the language of space-time, and as we listen, the universe reveals that it might not be a fabric at all, but a chorus. Billions of voices forming a structure that sings its own existence. Finding the atoms of space-time is the next frontier. It is the threshold Einstein could not cross, the doorway to a unified understanding of nature, the answer to how the universe builds itself. If gravitational waves are the majestic ocean swell of space-time, then the graviton is imagined as the tiniest drop within that ocean, a quantum of gravity, a particle that carries the influence of mass and energy the same way photons carry the influence of light. For many physicists, the graviton is not only a prediction, it is a necessity. If everything else in the universe obeys quantum rules, then gravity must obey them too. The wave must be built from quanta. The swell must come from droplets. Without gravitons, quantum physics and general relativity would remain forever separated. The graviton is the hoped-for bridge. To picture a graviton, imagine shrinking a gravitational wave until it cannot be divided further. You keep slicing the amplitude in half until you reach a final indivisible packet of vibration. That last packet would be the graviton. It would behave like a massless particle traveling always at the speed of light. It would come in only one form, a messenger of curvature itself. The graviton would not move through space-time. It would be the change of space-time. It would be the smallest yes or no by which gravity communicates. If we could ever detect a graviton, it would prove that space-time has a quantum architecture. Geometry would come in steps, not a continuous slope. But here lies the difficulty. Gravity is incredibly weak compared to every other force. A simple kitchen magnet can lift a metal key against the gravitational pull of the entire planet. That weakness means that a single graviton interacts with matter so faintly that no human detector can notice it. If you tried to capture a graviton by building a device huge enough and sensitive enough, the gravity of the device itself would collapse into a black hole. Nature hides gravitons behind its own laws. No known experiment can reveal a lone graviton, not even the most powerful collision of particles on Earth, not even the loudest gravitational wave from colliding black holes. Our technology hears the wave only in its collective form, like listening to the roar of a crowd without ever hearing one person speak. Yet the evidence for gravitons may come indirectly. If gravitational waves show the right kinds of quantized behavior, if their energy comes only in discrete jumps, that would reveal the pixels of reality. These pixels would be unimaginably tiny. The Planck scale is so small that if a single proton were the size of the Sun, the Planck length would still be smaller than a grain of dust. At that scale, the smoothness of spacetime would dissolve. The trembling of the quantum vacuum would dominate. Everything that appears calm at human size would become a storm of fluctuating geometry. Physicists sometimes imagine gravitons as excitations of a field that fills the universe. In quantum theory, every force has such a field. The electromagnetic field produces photons when disturbed. The strong nuclear field produces gluons. The gravitational field would produce gravitons. But gravity is special. It does not simply move particles through space. It shapes space. It shapes time. The graviton would not only carry a force, it would update the geometry of existence. If gravitons exist, then gravitational waves should not have any arbitrary energy. They should come in multiples of the graviton energy, but that quantum step is far too small to measure with current detectors. A gravitational wave signal that arrives at a laser interferometer contains an unimaginable number of gravitons. Counting them would be like trying to count drops in a waterfall while being swept away by the water. Sometimes scientists wonder if gravitons could show themselves in the cosmic background. Perhaps ancient gravitons remain from the fiery birth of the universe. They would form a gravitational analog to the cosmic microwave background. A cold symphony of the first vibrations to ever exist. Detecting this background would give us our earliest glimpse of the quantum structure of spacetime. But our instruments are nowhere near ready for that task. There is a deeper puzzle that gravitons could help solve. In quantum mechanics, forces arise through interactions of discrete particles. But gravity is not just a force. It redefines distance and duration. How can a particle decide what a meter is? How can a particle dictate the flow of seconds? The graviton would need to carry instructions about geometry itself. Every exchange of gravitons would rewrite the map of the universe in real time. If that is true, then the flow of moments may be nothing more than continual updates of the gravitational field. Time itself would be a bookkeeping of these updates. The graviton also challenges our idea of locality. In quantum theory, entangled particles influence one another instantly across great distances. If gravity is emergent from entanglement, then the graviton might not be a tiny ball traveling from one point to another. It might be a change in the layout of relationships, in a network too abstract to picture. The wave then would be the reshaping of the network. The graviton would be a flip in the connection pattern. The pixel would be a unit of information rather than a piece of matter. That idea brings us to a daring vision. What if the universe is a vast quantum computation? What if photons and electrons are bits and qubits of that computation? And what if gravitons are the operations that rewrite the memory of the universe? In that picture, the cosmos computes its own geometry. The graviton would be a step in the algorithm. The gravitational wave would be a large-scale program update. When stars collide and space rings, the code is rewritten. The universe edits itself. Gravitons may also hold the key to unification. The dream of physics is a single theory that describes all forces and all particles. If gravity has a quantum particle, then it can join the other forces on equal footing. The puzzle pieces would finally fit. The war between general relativity and quantum mechanics would end. We would no longer require two incompatible languages to describe one reality. The graviton would translate between them. But science demands patience. We cannot claim gravitons exist until a measurement confirms their influence. For now, gravitons remain hypothetical, mathematical ghosts that lurk in equations. Yet their existence feels almost inevitable. The universe has been quantized at every turn. Energy, charge, angular momentum. Why should gravity alone escape quantization? The search continues not in laboratories alone, but in the deepest corners of the sky. Gravitational wave observatories listen. Space telescopes scan for relics of ancient vibrations. Particle physicists look for clues in collisions. Theoretical physicists push mathematics toward the limits of imagination. All share the same ambition. to see the pixels of space-time. If we find the graviton, we discover the first true building block of geometry. We learn that space is not a stage, it is structure. We learn that the universe is not a smooth arena. It is a grid of information refined into a continuum by sheer scale. We learn that every ripple in reality is made of tiny quantum choices. To detect a graviton would be to hear the smallest sound the universe can make. It would confirm that space-time is built, not merely present. And that discovery would place humanity on the threshold of a complete physics. A physics that explains the birth of time, the shape of the cosmos, and the destiny of every star. The graviton waiting to be found may be the most important particle in existence, the pixel of reality, the tiniest heartbeat of the universe. There is a bold idea reshaping the deepest levels of physics. It suggests that space is not truly a distance. Time is not truly a flow. Geometry is not truly a thing. Instead, everything we call space-time might emerge from a far more mysterious ingredient: quantum entanglement, the invisible connection that links particles instantly across cosmic distances, may be the very thread that weaves the universe together. In this picture, entanglement is not a feature inside space-time. Entanglement is what creates space-time. To understand this, imagine separating two quantum particles after they interact. Measure one and the other responds instantly, no matter how far apart. Einstein disliked this phenomenon and called it spooky action at a distance. Yet experiments show the effect is real. The universe does not care about separation when entanglement is involved. Information flows without traveling any path at all. This breaks the ordinary idea that distance defines how things influence one another. Perhaps distance is not fundamental. Perhaps distance is only an illusion created by how strongly things are entangled. A striking proposal by physicist Mark van Raamsdonk argues that if we reduce the amount of entanglement in a region, the geometry of that region stretches and tears. Space grows looser and eventually disconnects. When we increase entanglement, the geometry repairs itself and regions join together. In this view, the shape of space-time is simply the pattern of quantum relationships. Smooth geometry is the result of an ocean of entanglement linking everything to everything else. Remove the entanglement and the ocean dries up, leaving no space-time behind. This idea inspired an extraordinary connection. Wormholes and entanglement might be the same thing described differently. Juan Maldacena and Leonard Susskind suggested that whenever two particles become entangled, they may be connected by a hidden tunnel of geometry, a tiny wormhole. The tunnel would not allow travel or communication faster than light. It would not be a science fiction doorway. It would be a symbol of how quantum information connects distant locations. Einstein-Rosen bridges and Einstein-Podolsky. Rosen entanglement become two sides of one truth. Geometry and information are linked. If this concept is correct, then gravitational waves are more than deformations of spacetime. They are changes in the entanglement network. Every ripple is a shift in how the universe keeps track of its own information. When black holes merge and gravitational waves fly outward, those waves may be carrying updates about how the web of entanglement reshapes itself. Gravity becomes the choreography of quantum relationships. In this vision, space-time becomes comparable to a woven fabric of correlations. The tighter the weave, the closer events appear. The looser the weave, the farther apart they become. There is no need to imagine a container in which matter sits. Matter and geometry become complementary expressions of the same quantum structure. The boundary between something and nothing dissolves. Even emptiness becomes a kind of fullness, packed with hidden connectivity. This approach also helps explain why black holes have entropy. When matter falls into a black hole, entanglement between the inside and outside changes. The surface area of the horizon measures that change. More area means more entanglement. More entanglement means more microscopic degrees of freedom. The horizon becomes an information boundary. a cosmic ledger where nature keeps accounts. Gravitational waves interacting with a horizon might disturb this ledger. The response might reveal the smallest signatures of space-time structure. Time itself may emerge from quantum entanglement. In quantum theory, evolution is simply the transformation of states. If the universe is one giant entangled state, then time might be the measure of how that state updates. The arrow of time would arise because entanglement tends to increase. The cosmos constantly spreads information outward. New links form. Irreversibility grows. The future is the direction in which entanglement deepens. This idea transforms our interpretation of motion. When something moves from one location to another, what really changes is how it is entangled with its surroundings. Position would be a measure of shared information. The shortest path between 2 points would be the path requiring the fewest updates in the entanglement pattern. Geodesics, the straightest lines in curved spacetime, would simply be the most efficient paths through the network of information. The elegance of this picture is undeniable. It unifies Einstein's smooth curves with quantum inseparability. It explains why spacetime is flexible. It explains why geometry contains energy. It explains why black holes behave like thermodynamic objects. It explains why gravity feels like a force, yet acts like curvature. But beauty is not proof. The theory must pass tests. And gravitational waves may become the first real test bed. If waves are vibrations of an entanglement network, then under extreme conditions, the network might respond imperfectly. Perhaps the wavefront becomes slightly scattered. Perhaps signals carry memory of exotic connections deep within black holes. Perhaps collisions of massive objects temporarily alter the connectivity of distant regions. Observing such effects would reveal the granularity of entanglement beneath smooth space. There may also be signs in the cosmic microwave background or in the distribution of galaxies. If geometry is built from entanglement, then the earliest structure in the universe would reveal its blueprint. Primordial gravitational waves might display patterns that directly correspond to how the entanglement web was seeded at the birth of time. This viewpoint leads to a profound shift in our cosmic identity. If entanglement is the raw material of reality, then every object in the universe is part of a single connected quantum state. We are not separate pieces drifting in emptiness. We are threads in the same tapestry. The feeling of distance is a convenient illusion. The true connection is deeper than space. When space-time becomes uncertain at the edges of a black hole, it may not be geometry failing. It may be entanglement reorganizing. When gravitational waves echo through the universe, it may not be the ringing of a fabric. It may be the flow of information updating the world. When stars collapse and new horizons form, the quantum ledger keeps track of how reality reshapes itself. This is why the search for deeper structure continues with urgency. Because if geometry emerges from entanglement, then spacetime is not the ultimate truth. It is a shadow of something more fundamental, something that does not care about here or there, before or after, something that defines existence through connection rather than location. Gravitational waves might one day allow us to peek beneath the shadow. They might show that the universe is not made of space, but of relationships. That reality is not measured in meters or seconds, but in linked information. That the cosmos is not a stage, it is a network dreaming itself into form. Gravitational waves are the messengers that come from the farthest reaches of time. When black holes collide or neutron stars spiral into one another, the waves they release carry the story of that moment across billions of light years. They travel unchanged through the vacuum because nothing can block or absorb them. They are the purest signal the universe allows. If we learn how to decode them, they will become instruments of cosmic archaeology, tools to uncover the earliest layers of existence. Everything we have seen so far are waves from the modern universe, recent collisions, recent explosions. But long before stars formed, before galaxies took shape, before atoms existed, the universe itself may have produced gravitational waves. During the first fractions of a fraction of a second after the beginning, the cosmos is believed to have undergone a burst of expansion known as inflation. Space grew faster than light could travel, stretching tiny quantum fluctuations into enormous patterns. Those fluctuations would have created a sea of primordial gravitational waves. They would be the oldest signals ever produced, older even than the light of the cosmic microwave background. Finding these waves is like searching for the first echo of creation. They would tell us how the universe behaved at energies beyond anything we can recreate. They could reveal whether space-time was smooth or already granular. They could show whether additional dimensions played a role in shaping the infant cosmos. They could even carry hints of unknown forces that acted only in those earliest instants. We search for these ancient waves indirectly. As they pass through the universe, they twist and swirl the polarization of the cosmic microwave background. The pattern they create is delicate, a faint spiral signature hidden among the noise. Many experiments have tried to detect it. Balloons flying high above Antarctica, telescopes placed at the cold edges of the Earth. Soon space-based observatories will join the search. A single detection would open a new chapter in cosmology. The next frontier of observation lies far from our planet. The Laser Interferometer Space Antenna will place mirrors separate by millions of kilometers in orbit. Using lasers to measure their separation, it will listen for slower, deeper gravitational waves than those detected on Earth. These waves may come from supermassive black holes merging, from clusters of compact stars interacting, or possibly from exotic phenomena such as cosmic strings, hypothetical defects in space-time formed in ancient phase transitions. If those strings exist, their snaps and vibrations would release gravitational waves across the sky. Detecting such a signal would reveal not only the physics of the early universe, but also the architecture of space-time at its birth. Gravitational waves may also expose what lies in the hearts of neutron stars. These stellar remnants pack more mass than the Sun into a sphere no wider than a city. They are the densest known objects that have not collapsed into black holes. When they collide, they ring like cosmic bells before falling silent. The tone of those rings depends on the behavior of matter under crushing pressure. Hidden within those tones may be signs of quarks freed from their confinement, forming a soup of fundamental particles. Some theories even suggest fragments of space-time structure might show themselves in these extreme environments. We can also look for continuous waves emitted by rapidly spinning neutron stars that wobble even slightly. These steady signals would allow incredibly precise measurements over long periods. Any deviation from perfect smoothness in the wave might reveal graininess in the underlying geometry. New observatories on Earth are preparing to deepen the search. As sensitivity improves, we expect to detect hundreds of black hole mergers each year, then thousands, then tens of thousands. With so many signals, we will be able to build a map of space-time properties across cosmic distances. Subtle evolutionary changes might become visible. Perhaps the earliest black holes formed differently. Perhaps their shapes and spins carry evidence of the first quantum influences on geometry. Every gravitational wave we detect is a clue. It is a fossil of motion and matter. The universe stores its history not only in stars and galaxies, but in the structure of space-time itself. Gravitational waves unlock that archive. They reveal events long vanished. They allow us to observe what no light can show. The promise is enormous. If we listen closely enough, we may discover that the familiar picture of the universe is incomplete. We may find that space-time at the smallest scales does not behave like a surface or a field, but like a network of information. We may uncover evidence that geometry was born in a quantum storm at the dawn of time. Cosmic archaeology is not about dust or bones. It is about the deep roots of existence. It is about understanding why gravity has the strength it does, why particles have mass, why the cosmos expands, why time flows forward. All of these mysteries might be encoded in the primordial waves waiting to be heard. The universe is ancient, yet it continues to speak. each gravitational wave is a syllable in the story of creation. We have learned the first words. Soon, we may learn the sentences. And perhaps one day, we will understand the entire language. There is a principle in modern physics so surprising that it changes the meaning of space itself. It says that everything inside a region of the universe can be completely described by information stored on its boundary. This is called the holographic principle. Just as a two-dimensional hologram can encode a three-dimensional image, the universe may encode its three-dimensional volume using data imprinted on a surrounding surface. In this astonishing picture, what we see as a rich interior world of stars and planets might actually be the unfolding of information from a lower-dimensional cosmic horizon. This idea first emerged from the study of black holes. When matter falls into a black hole, the horizon grows. From the logic of thermodynamics, that growth means an increase in entropy, which counts the number of possible internal configurations. Strangely, that entropy depends only on the horizon area and not on the volume inside. That discovery hinted at something revolutionary. Black hole horizons behave like sheets of information. They know everything swallowed by the hole. They encode the details of matter on a surface instead of storing them inside a deep interior. Physicists wondered whether this was just a trick of black holes or a universal rule. It turned out that something similar may apply to the entire cosmos. If space emerges from quantum information, then perhaps all of three-dimensional space-time is like a projected image. Our everyday world might be the holographic display of a deeper law of nature that lives on the boundary of the universe. Now imagine gravitational waves in this context. They ripple not only through space, but also through the information that defines space. If the volume we inhabit is a kind of holographic screen, then every gravitational wave is a change in the message written on that screen. Waves record new data about mass moving and merging in the cosmos. They update the boundary that gives rise to the interior. What we call curvature in 3 dimensions becomes information flow in 2. The most detailed realization of this idea so far is the correspondence between a gravitational world in something like anti-de Sitter space and a quantum field theory without gravity on its boundary. Physicists work hard to make this correspondence useful for our own universe, which expands rather than curls. Yet the direction is clear. Gravity might not need to exist within a volume at all. It might arise because the surface cannot hold its shape without bending the space it projects. If that is true, then the universe is not like a balloon floating in a larger space. It is like the image projected from the balloon surface itself. All that exists would be encoded on the cosmic horizon, the boundary between what we can see and what lies forever beyond. As the universe expands, that boundary changes. More information arrives as new regions become visible. The interior grows, not because new space is created, but because the hologram adds new data. This is a breathtaking shift in perspective. It means that distance inside the universe may be an emergent feature rather than a fundamental one. It means that positions are just coordinates in a code. It means that gravitational waves are fluctuations in the coding of reality. When 2 black holes collide, the burst of gravitational radiation is like a rewrite of the cosmic script. The boundary updates reflect the change in entanglement relationships throughout the entire universe. The holographic principle also suggests that there is no such thing as an absolute here or there. What matters is how information is linked. If the boundary knows everything happening inside, then the fabric of existence is a single unified record. The universe becomes a living archive where information never truly disappears. Even when matter falls into a black hole, the horizon keeps its memory in subtle changes of area and structure. Perhaps the most tantalizing idea is that holography implies space-time itself is a storage system. Geometry is the format in which information is written. Gravitational curvature is the cost of storing that information. Where energy and mass exist, the geometry bends, because the universe must allocate more room in its ledger to record the complexity of interactions. Gravitational waves then would be the motion of information across this cosmic ledger. They are not mere disturbances in a silent void. They are signals in a universe that remembers. They are lines rewritten in the code that creates reality. They are the news reports of matter and energy events, broadcast onto the edges of space. Some researchers are attempting direct tests of holographic ideas using gravitational wave detectors. If space-time is not perfectly continuous, but instead an encoded surface projected into a volume, tiny irregularities in that encoding might become visible. Light traveling along the arms of a detector might show extremely slight and random fluctuations in distance. These fluctuations would not be caused by noise, but by the finite and discrete nature of the geometry itself. Several experiments have looked for such effects. None are confirmed. Yet the very act of searching brings us closer to the deepest truth of reality. If holography is correct, then the universe is a marvel of efficiency. It compresses information into the smallest possible package while giving rise to a world that feels spacious and rich. 3 dimensions are an illusion created by a 2-dimensional foundation. Gravity is the stagecraft that makes the illusion convincing. To understand this is to appreciate gravitational waves on an entirely new level. They are not just tools that let us observe the universe. They are clues to how the universe is built. They may reveal that everything we see is encoded beyond the horizon of our perception. They may show that reality is a hologram where the edge determines the inside. And if that is the case, then space-time is not what it seems. It is a projection, a structure woven from information, a dynamic memory remembering every cosmic event. Gravitational waves are the messages written into that memory. When the cosmos vibrates, the information on the boundary updates, and a new version of reality emerges within. Chapter 9. When space-time is the signal. There is a daring possibility emerging from the convergence of quantum theory, relativity, and information science. It suggests that what we have been calling space-time is not a container at all. It is not a stage where the universe performs. It is the performance itself. And gravitational waves are not disturbances traveling across a pre-existing arena. They are updates to the rules that define that arena. In this radical interpretation, the universe may not be made of matter in space. It may be made of information that creates the illusion of space. If this is true, then the gravitational field is not a force acting inside existence. It is existence. Every change in gravitational energy becomes a direct change in what distance means, in what duration means, in what separation means. When a gravitational wave travels, it does not move through space. It changes the relationships that give rise to space. The wave is the geometry. It is a reorganization of the network that defines where and when events occur. To see why this idea is even considered, think about motion. When an object moves from one place to another, what actually changes? It is not the object itself. Its identity remains. What changes is its relationship to other objects. In a background-free physics, position is nothing but a set of relationships. There is no absolute here or there, only patterns of connection. Geometry is relational. Space is the catalogue of how things relate. Relativity already points us in this direction. Einstein showed that clocks tick differently depending on motion and gravity. Rulers measure differently depending on how mass curves space-time. There is no universal grid. The universe does not provide coordinates for us. We impose them for convenience. Physics cares only about how objects influence one another. If geometry can change based on those influences, maybe geometry is not fundamental. Maybe it is the result of those influences. Quantum theory pushes even further. Entanglement creates instant connections between distant particles. The strength of the connection defines how much information can flow. If distance can be defined by how entangled two systems are, then geometry becomes a measure of information connectivity. Where entanglement is strong, space feels short. Where entanglement is weak, space feels wide. If entanglement disappears, so does space. Combine these insights, and the picture becomes clear. Space-time could be the structure of information. It is a map drawn by the universe to keep track of how everything is related, and gravitational waves are the corrections the map makes when the relationships update. When stars collide, information about their mass and motion changes everywhere. That updated information propagates. The change is what we detect as a wave. In this view, the smallest pieces of reality are not particles or loops or strings. They are units of information. Bits or qubits. They do not sit inside space. They generate space. They do not evolve in time. They generate the sense of time passing. The fabric of reality becomes a dynamic computation. And gravitational waves become the broadcast signals of that computation updating itself. This idea has profound implications for the arrow of time. Information in the universe tends to spread out and entangle. That process is difficult to reverse. The increase of entanglement gives rise to a direction of time. The future is simply the direction in which the universe's information grows more connected. Gravity, which shapes motion and collapse, drives this increase. When a star collapses into a black hole, its information becomes scrambled across the horizon. When gravitational waves leave a collision, they carry relational information outward, increasing the total connectivity of the cosmos. If space-time is information, then a black hole is not a hole at all. It is a memory system. Its horizon is a screen that displays the state of all matter that has fallen in. Gravitational waves hitting the horizon modify that screen. The screen responds. Even evaporation of black holes becomes the release of information back into the universe, written into radiation that encodes the hidden degrees of freedom. Nothing is lost. Existence keeps its own accounting. This concept also changes how we think about the end of the universe. If all of space-time is information, then the destiny of the cosmos depends on how information evolves. It might dissolve if entanglement networks weaken. It might reboot if a new informational structure emerges. The universe could collapse not into a singularity, but into a phase change of information. A new space-time could form with different rules. The death of geometry might be only a transformation of data. Gravitational waves would be the fingerprints of such transformations. They might one day reveal shifts in the fundamental operating system of reality. Subtle changes in propagation speed, unexpected interference patterns, behaviors that cannot be explained by smooth geometry. Each anomaly would be a signal that space-time is not what it appears, that beneath the familiar distances and volumes lies a world built from logical relationships. This view leads us to a remarkable philosophical realization. The universe is not a place, it is a process. A continuous updating of connections, a computation that never pauses, a story that writes itself. We are inside the story, part of the script, yet also the means through which the story understands itself. Conscious beings able to reflect on the architecture of existence become agents within the very information they explore. If space-time is the signal, then physics becomes the decoding of that signal. Observatories become ears pressed against the cosmos. Gravitational waves become the spoken language of creation. They carry meaning. They carry structure. They carry the evolution of everything that has ever happened. When we detect them, we are not merely observing distant events. We are witnessing the universe update its own identity. And so the search continues. With every detection, we sharpen our understanding of the signal. One day, with greater sensitivity and deeper listening, we may hear something new in the waveforms, a slight break in smoothness, a whisper of discreteness, a rhythm that hints at the code beneath the stage. That will be the moment we uncover the fundamental layer, when space-time reveals that it is not the ground of existence, but one of its most beautiful illusions. From the smallest whisper of a quantum fluctuation to the roar of colliding black holes, the universe seems to be telling one continuous story. It is a story in which space-time is not a passive arena, but an active character. A story in which gravitational waves are not disturbances of a medium, but the medium discovering new forms. A story in which the cosmos does not merely evolve inside geometry. The cosmos evolves geometry itself. In the deepest interpretation, the universe is building its own foundation every moment. Einstein gave us the first glimpse of this truth when he revealed that mass and energy tell space how to curve, and curved space tells matter how to move. But his equations treat spacetime as smooth and continuous. They do not reveal what happens when curvature reaches extremes or when distances shrink to nearly nothing. Quantum theory, on the other hand, demands discreteness. It claims that nothing can change in infinite detail. Reality comes in finite steps. Somewhere between these principles must be the architecture of spacetime. Our journey has explored many ways such an architecture might appear: strings vibrating in hidden dimensions, loops linking to form quantum geometry, entanglement weaving distances into existence, information stored on cosmic boundaries projecting the world we know. Each idea offers part of the truth. Perhaps none alone is the full answer, but together they point toward a single unifying insight. Spacetime may be emergent, not a fundamental ingredient of nature, but the product of more primitive relationships. Gravitational waves are the clearest sign that this is possible. They show that geometry can ripple. They show that distances can change. They show that the structure of reality is dynamic and alive. A rigid backdrop would not allow such music. Only a living foundation could vibrate this way. When we listen to these waves, we hear the universe process information about itself. If the universe is emergent, then time becomes the measure of emergence. The forward flow of time could be a direct consequence of increasing entanglement and structure. What we call the past is a state of lesser connectivity. What we call the future is a state of deeper connectivity. The universe is not moving toward disorder. It is moving toward complexity, toward richer geometry, toward a grander self-understanding. This perspective changes how we see creation. The birth of the universe may not have been a sudden explosion into pre-existing space. It may have been the moment when space-time itself first crystallized out of pure quantum potential. The Big Bang would be the beginning of relationships, the formation of connections, the switch from a world without location to a world that can hold stars and atoms and life. And the end of the universe, if it comes, may be equally a transformation. As structures fade and energy disperses, the entanglement network might weaken. Geometry could dissolve. Distances could lose meaning. Time could lose direction. The universe would not vanish. It would shift into a different kind of existence where the rules we know no longer apply. Gravitational waves may guide us all the way through this grand arc. They may reveal how the first seeds of geometry emerged. They may show how the architecture evolves over billions of years. They may even warn us when the structure begins to decay. In a sense, the waves are the heartbeat of the universe. Every pulse is a reminder that the cosmos is not static. It is constantly updating, learning, building itself from the inside out. The dream of physicists is to discover a single principle that unites all these ideas. A principle that explains why space-time exists and how it arises from deeper forms. A principle that predicts what geometry becomes at the smallest scales. A principle that reveals how the very large and the very small meet in harmony. When that principle is found, humanity will finally understand the script of reality, instead of only reading the lines as they appear. Yet perhaps the greatest revelation comes not from the mathematics, but from what it implies about us. If we are made of the same relationships that create the structure of space-time, then we are not separate from the universe. We are part of its fabric, part of its information, part of its continuing formation. When the universe builds itself, it builds us. When geometry evolves, our own existence reshapes. We are participants in creation, not mere observers. Gravitational waves bring us closer to this truth. They allow us to listen as the universe speaks. They carry messages from phenomena far beyond the reach of light and show us that reality has layers we are only beginning to uncover. They suggest that the void is not empty, that the simple is not simple, that existence is profoundly interconnected at every scale. So we arrive at the frontier. Beyond it lies the true nature of space-time. The question that has echoed through physics for more than a century now crystallizes. Is space-time built from gravitational waves? Or are gravitational waves the sound made by space-time as it builds itself? The answer might be both. The universe may be a grand feedback loop where geometry vibrates and those vibrations refine geometry. A cosmos that is not content to simply be, but endlessly strives to become. In the end, one idea rises above all others. Space-time is not the stage of the universe, it is the performance. And gravitational waves are the music holding it together.